Hello and welcome to lesson number 6, and we're talking about arc length. Arc length. So we've talked about, we know what an arc is. Now I want to be able to have it so that you can calculate the length of that arc. So what's the goal today? You can determine the arc length of a circle. All right, so that's what we are looking at today, and we are looking at a central angle, not a subtended angle. So I'm just going to, should be a central angle. All right, so here we go. So, formula for calculating arc length. So we're looking at being given a radius. And for those that don't remember this, in a circle, if I start at this radius and I go all the way around and back to the start, that's 360 degrees. So if I wanted to find the area of the whole circle, area would equal pi r squared. Okay? But we don't want the whole circle. We want a sector of it, a pi piece. Now, in order to get your pi piece there, we would have had to move, and I'll do this radius. We would have rotated it to this location. So we moved it some angle, all right? And theta is the variable that we let represent angles. So up here, we call it theta, and it represents a missing angle. So it's just a Greek letter that we've picked in math to say this is a missing angle, or it's an angle that we want. And we also know this is a radius and this is a radius. So what we're looking at is we're looking at some proportion of the circle. So instead of wanting the entire area of a circle, okay, that would calculate the entire area of a circle, we only want a small segment of that circle. All right, we want to find some mid-proportion to it. So the relationship that we want to find here, we're looking for arc length. So I put the formula for area of a circle up here. So that's the full circle. And circumference is 2 pi r. That's our circumference. I'm not going to go into all of the details with the ratio, but we are looking at a ratio of, and we haven't talked about ratios, but it's I'll just put it's a relationship between area, circumference, and radius to give, and I'm just going to give you the final formula here for arc length. Okay, so we're going to use capital L for arc length, and it is going to be our formula. I want to make sure I use the right one. The resulting formula would be pi r theta over, or divided by, 180 degrees, or pi times radius times the angle divided by 180. Okay, so there is our formula. I'm going to give us a legend here in a sec. So legend, capital L is your arc length. Small r is radius. And theta is the angle in degrees. All right. So we are finding this formula here is calculating this distance. Okay. So this is our L. So we're finding arc length. All right. So Determine the given arc lengths. So what are you given in the homework? You'll be given a radius and an angle. So for example, it'll say 5 centimeters and an angle of 100 degrees. So you calculate it. You know that you're looking for arc length. Arc length is going to be the length of the curve contained or matching up with the corresponding angle. So the 100 degrees is there. So that's the arc length we would be looking for. So L equals pi times r times theta divided by 180. So 3.14 times the radius is 5 times 100 for my angle divided by 180. So bringing up a calculator again. Clearing that. 3.14 times 5 times 100, and then divided by 180 equals 8.7. 8.7. What units am I working with? Radius is in centimeters, so your answer always comes out to be the same units that you were using originally. All right. Second example. What happens if the angle is on this side? So what happens if we were looking at 300 degrees? And I'm going to tell you the radius was 10 meters. The answer is nothing changes. The only thing you have to recognize is that the 300 is on this side, so this is the arc length that we're actually calculating right there. So for my second example, pi times r times theta divided by 180. So it'd be 3.14 multiplied by the radius, which is 10, multiplied by 300 divided by 180. So we use our calculators. So 3.14 multiplied by 10 multiplied by 300 divided by 180. We get 52.3. 52.3 meters. So if you were to walk from here and go around the outside to here, you would have walked 52.3 meters. So we're calculating the distance around part of a circle or part of the circumference. Final two examples here. So we have a horseshoe. Horseshoe is made from a piece of circular steel as shown. So it's kind of an approximation for us because we assume that the horseshoe is cut from a piece of circular steel. So on the diagram, I would give you this information. I would tell you that that angle there is 325 degrees. And I'd have to give you the radius. So let's give a radius of 10 centimeters. So if we want to know how much of that steel you're going to use, what we're really looking for is the length around here. And this will give you an approximation. It's not going to be an exact value because the circle or the horseshoe is not a perfect circle, but it's going to give you an approximation as how much steel you would have to bend into a circular shape. So we're looking for an arc length. So we are using the formula we just talked about. 3.14 multiplied by the radius is 10, and the angle is 325 divided by 180. Using our calculators, 3.14 multiplied by 10 multiplied by 325 divided by 180 would give us 56.7. So 56.7 meters. So therefore, the shoe uses 56.7, oops, that should have been centimeters of steel. So the distance from edge of horseshoe all the way around to edge of horseshoe is 56.7 centimeters. A belt is in contact with a pulley. So we have a pulley here, and pulley has a radius of, let's go with 20 centimeters. So here's my belt, okay? So it's like on a lawnmower, okay, or in a snowblower, or maybe in a car. So the radius of that pulley that's spinning around in circles is 20 centimeters. This is our belt pulley. Determine how much of the belt touches the machine, or touches the pulley when the machine is running. So we want to know how much of the belt is in contact with this pulley. Well, it's only in contact with part of the circle or part of the pulley, and it's from here over to here. So we want to know that length right there. So how much belt is in contact with the pulley? So we are dealing with an arc length. It's part of the edge of a circle. In order to calculate that length, we would use pi times r times theta over 180. And of course, I have to give you the central angle. If I did not give you the angle on a test, you would use a protractor here. So I'm going to use a protractor in this case. Find my protractor quickly. Oh, I'm just going to pause, and I'm going to get a protractor to show you. All right, you'd be happy to know I found a protractor. So now I'm going to take my protractor, and I'm going to measure the angle here. So what I would need to do is I need to take a ruler, and I need to extend that green line there. And when I'm reading it off, I'm looking at that angle, so the angle from there to there, my protractor, I would say it's about 86 degrees. So the angle in there is at 86 degrees. All right. So going back to my formula then, 3.14 multiplied by 20 multiplied by 86 divided by 180. I can find how much of the belt's in contact with the pulley. So I'd end up with 3.14 times 20 times 86 divided by 180. And I'd find it would be 30 centimeters. So therefore, 30 centimeters of the belt is in contact with the pulley. Can't seem to spell pulley. There we go. All right. So that gives you an idea of how you're going to use arc length. So we'll deal with any questions you have when you come and see me.